Our next speaker and final speaker is Professor Jonathan Roberts, who's professor in robotics here at QUT. His main research interests are in the areas of field robotics, and in particular autonomy. He's also recently begun research in the area of medical robotics. Jonathan was co-inventor of the UAV Challenge, an international flying robot competition that sees teams search for a lost bushwalker using autonomous robotic aircraft. Before joining QUT, Jonathan was research director of CSIRO's Autonomous Systems Laboratory, where he developed projects in the area of museum robotics and telepresence. He's a past president of the Australian Robotics and Automation Association, and he currently serves as a senior editor of the IEEE Journal of Robotics and Automation Letters, and as associate editor of the Journal of Field Robotics. And Jonathan will be talking to us today about making robots that can see. Please join me in welcoming.
Okay, making robots that could see. Now, how do I move the slides on? Just this button? Brilliant. Okay. So does anybody, first of all, know what computer vision is? We're going to talk about robotic vision in a bit, but computer vision first. No one here? Oh, okay. Oh, of course you know, Graham. That's right. All right. So computer vision. So computer vision is where we have maybe a camera and a computer, sometimes a simple computer, and the computer does some basic processing on that picture and maybe identifies a few things. Now, I've given you a few clues. Can anyone identify an example of computer vision? Do you know where it's been used on you today? Because it's probably affected you today, even though you might not realise it. Anyone can think about any ways that they've been influenced by computer vision? Over there? Yeah, face tracking, that is a really good one. So here are some examples. So you can see in the bottom left there, when you take a photo on your smartphone, you'll see this little box come around where there's a face. So there is computer vision systems built into all of your phones. You'll find there's computer vision systems in pretty much all car parks now. So when you go and park, you'll notice there's a little camera. When you press your finger and get a ticket, there's actually a camera taking a photo of your license plate. This is for security, so that when you go out, it cross-checks it and will only let you out if you've got that ticket with that car. And this is all happening without many people realising. If you go and look at some of your parking tickets now, you'll see printed on the ticket is your license plate. And that's because a computer vision system is watching your car as you drive in, and it already knows your number of your car, and it prints it on the ticket when you press the button. So this is all happening, a few seconds before you even press the button. Other examples are, of course, at airports. So you might not realise that bottom one, but as you kind of walk out of the aircraft, and they like you to walk fairly slowly, and a lot of airports don't like these travelators where you go too fast. So they deliberately make you walk slowly in some places so they can scan your face. So there's a lot of security going on. They're checking who you are. So before you even turn up with your passport, they know if you're one of the baddies or not. Right? So it's all happening without you realising it, and there's no human intervention here. An alert will just go off that you might be one of these dodgy people. And then you've probably all been through these e-gates at the top, these passport control systems where now you don't even see a human. So if you've kind of been flagged as okay as you're walking off the plane, then you'll probably get through that top gate quite easily as well. But there's other ways that computer vision sort of influences your life. And the next one will probably blow you away, because you probably won't realise that every grain of rice that you eat has been actually looked at by a computer. This kind of amazes a lot of people, but if you look in a bag of rice, you will find that it's very consistent. All those grains the grains of rice in a bag of rice all look pretty much the same. They tend to be the same colour and the same shape. Now, that's not because these plants are very consistent at growing the rice. It's because there is a computer vision system that actually images every single grain of rice and sorts them into like bins. So all the grains of rice that are a certain shape and a certain colour go into one bucket, and all the grains of rice are another shape and another colour go into another, and then they're all used in different ways. And all the tiny bits get smashed up and used in sort of flour, rice flour, etc. So a lot of your food that you eat is actually sorted by a computer vision system. And of course it happens very quickly. So you can see here all these grains of rice are sort of falling down this chute, and what you can't see in this machine is there's a whole range of cameras. All of these grains go into little funnels, there's cameras, there's little computers, and it's measuring the size and colour of all of those grains of rice, and then there's little doors that sort it out, and then it all comes out the bottom all fully sorted. And then gets sort of batched up. And this is happening to all of your rice. So did anyone eat rice in the last few days? Yeah, there you go. So that was all probably sorted with computer vision system. And there's lots of these examples, particularly in food processing, which is why a lot of food's getting very sort of consistent look because it's actually sorted. So let's move on to robot vision. So robot vision is a thing we're interested here at QUT. And this is kind of the dream robot. Does anybody here want one of these robots? Yeah, that's right. Okay. So as you can see, this robot is, this video is sped up 8 times. It doesn't really work this fast. But if you weren't at home, then if it was 8 times slower than this, who cares? You know, if you're at work, the kids are at school, it can tidy up for you. And when you come home, it's all done. Now, what you didn't realise in this, let's go back and just play it again while I speak, is actually there's a human controlling this who's off to the side, looking through the cameras on this robot, and they're controlling it from using a remote control system. So the tragedy of our world is we can't have a robot like this yet. We can physically build a robot that looks like this, but we don't have the robot vision systems for a robot to actually identify everything in that scene or even figure out what to do. We still really need a human to do this. So people often ask us as robotics people, have you got a robot that can fold the washing yet or do all these household chores? It turns out that doing that is actually harder than almost anything else. So unfortunately, these sort of super domestic robots that will be able to do everything you want them to do are kind of a long way off. We'll see robots in a lot of other places before we see these, and that's because of robotic vision. Robotic vision is a very difficult thing to do. So here is a quick one slide on how a robot works. So if you look at this loop here, we have our robot on the right, and you'll be able to play with one of these a little bit later. We have this loop, which is known as the sense, think, act loop. So you can see sensing. So vision is one of the senses. Of course, some robots hear. This robot you'll see later when you get to play with it. If you talk to it, it will turn its head. It will move towards sound. But vision is a very important sense for robots. The reason it's so important is really because you can get a lot of information from an image. It's also relatively cheap in the sensor itself, but the complexity then goes in how do you make sense of the world. So a typical robot does this. It takes a photograph, that's passed to a little computer system. There's some algorithms in that computer that analyse the picture. They then send signals to the motors of the robot. The robot does something to the world, and it then goes back and takes another picture. And this would typically happen maybe 50, 100 or 1,000 times a second. So this is a constant loop that is going around. And when people then say, well, what is seeing? What does seeing really mean? It's a complicated business. So seeing isn't just sensing. It's not just grabbing a picture. It's that whole rest of it. It's the thinking. It's the moving. The robot has to move itself in order to maybe see something else. We can sort of seeing is much more than just analysing one simple picture. Analysing one simple picture is what we call computer vision, and then robotic vision is where you're actually live and interacting with the world. And this is the complexity that we have at the moment, and this is what's holding robotics back. So robotics has kind of hit this plateau where we're not going to go much further until we crack this seeing problem. So we're very lucky in Australia. We have a lot of the world's leading lights in robotic vision, and last year we were awarded lots of money by the ARC, and QUT leads a thing called the Australian Centre for Robotic Vision. And this is a 4-university organisation. So we have ourselves, QUT, Monash, ANU, and the University of Adelaide. And that will run for 7 years. And its mission is to try and crack this problem of seeing by robots. Now, we're not naive. We probably won't solve all the world's problem in seeing for robots, but we're trying to crack some of the major problems. So I'm now going to give you just a quick few examples of how we're using, what sort of problems we're using to crack these problems. So we're developing some farm robots here at QUT. You can see a picture of one here. The scale of this robot is probably, it probably goes from where I am here to the edge of the stage. It's probably to the edge of the stage over there. It's probably that kind of scale. These are electric vehicles. And the heart of this robot is a vision system that is looking down at the crops. So the idea of this robot is it's a weeding robot. So as the crops are growing and as the fields are left maybe fallow before the new crops come in, these robots are roaming, sometimes at night, and they're actually looking for the weeds. And then robot arms under this robot actually come down and zap the weeds. So this is kind of a weed killing robot. So it is a killer robot. People often don't like killer robots, but this is a good one. It's killing weeds. The idea of these sorts of robots is that you can change the whole farming method and remove the inputs in farming. So typical inputs in farming are things like diesel or herbicides. So when you weed, you've got to fill the tractor with diesel and you've got to put herbicide in, which gets sprayed on the weeds. The idea of using a robot to do weeding is you can do everything just by the power of the sun. So we can have electric robots that are solar powered, and we can zap the weeds with an electric current on a robot arm, or we can use an electric robot arm and rip the weeds out or smash them up. So the whole point is you can use the sun to do your weeding, and then you don't need diesel and you don't need herbicides, which would kind of revolutionise weeding. So we're thinking of ways to really improve efficiencies and kind of revolutionise farming. But the heart of this is getting a robot to be able to see. That's really the difficult part. Here's another killing robot. What you'll see, there's a theme. We seem to like killing robots. This robot kills crown of thorns starfish. So as everyone is probably aware, crown of thorns starfish is a big problem. They're sort of starting to destroy the Great Barrier Reef as the waters of the Great Barrier Reef are heating up, and as there are more herbicides and all sorts of things coming off the land. The crown of thorns starfish seem to be increasing in numbers, and they're very hard to control at the moment. So at the moment, divers have to go and patrol the Great Barrier Reef, and I don't know if anyone's noticed, but that's quite big, the Great Barrier Reef, and people are quite small. So it's actually never going to work. People won't be able to keep control of crown of thorns starfish. So really the only solution is to develop robots to do it for us. Nothing else is really going to work. So what happens here is currently humans, and I'll show you on the next slide, you'll see a video in a second, humans go and find them, they're divers, they go down, they look for a crown of thorns starfish and they inject it with a poison. This poison has been developed by James Cook University, and it's a special protein that only kills crown of thorns starfish. So if you accidentally stab something else, it's okay. It's also fully biodegradable, so it will disappear, and it's not bad for anything else. But crown of thorns starfish don't like it, and they die fairly quickly. You'll see this video here. So we might play this a few times just so you can get a handle on what's happening. You can see at the bottom here is a probe. It's going to lock onto a crown of thorns starfish and then inject it. Now, what's happened over the last year is all of the divers that have been killing the crown of thorns starfish have had a little video camera attached to their killing device. So every time a crown of thorns starfish has been killed, it's been recorded. And then what's happened is the researchers here have used a robot vision system, and they have trained a robot vision system to understand what a crown of thorns starfish looks like. So with all these many thousands of videos, the robot has learnt what a crown of thorns starfish looks like, and they now have an algorithm that's 99.99% accurate. And if you show it video and there's a crown of thorns starfish in there, it will lock on. It will then, we'll go back a slide and you'll see, it will deploy this robot arm under the submarine, and inject the crown of thorns starfish and then move on to the next one. This robot is very much a prototype, and it's undergoing its first reef trials starting next week. So it gets shipped up to Cairns next week, and it will start to undergo tests on the reef. It's been tested in Moreton Bay, locally to here, up until now. So we should know in a few weeks how successful it's been. Of course, then, if it is successful, then how many will be required? And, you know, all of these are unknown things at the moment. We have to prove the concept first that it can eradicate a large number of crown of thorns starfish in a certain region. But again, the heart of this is robotic vision. Without a vision system to find these crown of thorns starfish, this simply isn't possible. Let's have a look at the next one. This was mentioned when I was introduced. So this is a fascinating competition that we've been running since 2007. And this competition is all about saving this dummy here in the yellow shirt. So this dummy we call Outback Joe, and he is placed about 7 or 8 kilometres from an airport, and teams from around the world compete. They build robot aircraft, and they build robot vision systems that automatically find Outback Joe, and then they drop a water bottle onto Outback Joe, and whoever wins gets $50,000. And this competition has become a kind of a worldwide phenomenon. We run it here in Queensland. Up until now, we've run it just outside Kingaroy, which is a town about 3 hours' drive from here, which is peanut country. These are peanut fields you can see here. And you can see in this picture here a yellow water bottle underneath a parachute. And you can see in the picture, sort of in the middle bottom, there is a sort of a blue outline and a sort of a dot. That is Outback Joe. This is a photo from a team that first won the UAV challenge last year. They're a team called Canberra UAV. And they managed to successfully, after this competition, remember, ran from 2007, so it took until 2014 for a team to finally win. Over that time, we had over 2,000 competitors compete, and everyone up until that point had failed to solve this problem. There had 350 teams from all over the world, about 25 different countries, had never managed to complete this competition. But finally Canberra UAV did it. And they managed an amazing feat. They launched their aircraft. It then flew automatically. It then searched, and it flew about 100 kilometres of path before it found Outback Joe. It automatically found Outback Joe. They then have to tell us as the judges, these are the coordinates, and we just cross-check just in case we don't want them to drop it on a farmer, because this is actually completely normal farmland. So this isn't a special range. This is regular farmland with regular roads, with regular people going about their own business. We do tell all the farmers that we're running the competition, so they understand what all these robot aircraft are. But there is a chance that it would lock on to someone just going around their own business. And farmers these days tend to wear high-vis clothes as well in this area. So there is definitely a chance. So what their algorithm did is we told them that Outback Joe was wearing blue jeans and a high-vis yellow top. And they developed an automatic system that hunted down blue and yellow things that are together, which actually doesn't happen much naturally. So you don't tend to find blue and yellow things together unless they're Outback Joe. And then they know their altitude, and they know roughly how many pixels it should be, and they can then figure out that that's probably him. And then they go and we confirm the coordinates, and they drop the water bottle. What this team managed to do, quite amazingly, is their aircraft managed to drop the water bottle within 2.6 metres of Outback Joe lying on the ground. Which is quite an incredible thing. But the significant thing about this team is that they're a group of people from, I think the youngest member was about 18 or 19, and the oldest member is in his 60s. And they're all there. They're a community team. So they meet every Sunday. They fly together. They write all their software together. They open source everything. They have discussion groups. The rest of the world kind of come and give them advice. They give away everything they develop. So some of the other teams that also completed the mission but weren't as accurate We had 4 teams actually complete the mission last time, use some of their software. So there's kind of a movement has started of people sharing all their information and their data and their methods. And it's been a very, very successful competition. We've now launched a new competition. So next year, in about a year's time, there will be a competition where Outback Joe has now he's got his water bottle, but he's now very sick. He's told his doctor, and his doctor's asked for a blood sample. So the robot aircraft now has to find Outback Joe, land next to him. He then puts in a blood sample in a little vial, presses a button on the robot, and it then takes off and flies back. And it won't be in a nice field like this. It'll be in a place with trees around, rough ground. So these robot aircraft will have to come in, hover, land, do all this stuff. And the team launching it will be 10 kilometres away, so, over the horizon. So it's all enabled by robot vision. So we're not just developing robot vision ourselves, we're trying to get the community to also develop robot vision systems. And it's a great way of leveraging, actually, a lot of free labour. Of course, they won $50,000, but I'm sure they spent far more than $50,000 in their own time over the many years that they put into this. They were working full-time on this for 4 years. So it's a serious business. Okay, the very last thing I'm just going to briefly mention is our new work in robotic vision for surgery. So QUT is very lucky to have a number of surgeons on our staff. And particularly surgeons that work with arthroscopy of the knee and other joints. So has anyone here had a knee arthroscopy? There's usually somebody in the audience that's had one. This is a procedure where there's something wrong inside your knee, and the surgeon puts makes a few little holes, sticks a camera in on a long probe, and inserts a tool in there, and they see what's wrong, and they go and do a little bit of fixing up. It's actually a very difficult procedure. It's hard for surgeons to do. The latest research that's come out of Oxford shows that surgeons will take about 160 procedures before they're good. So, and those 160 procedures will happen on us, right? That's just the way it is. That's surgery for you. I mean, it's not in surgery. It's known as the learning curve, and each procedure has a different number in the learning curve. Some is much lower than that. Some surgeries is higher than that. But the research is showing it's about 160 cases per new surgeon. First of all, of course, they practice on plastic models. Then they tend to practice a little bit on cadavers, so people that have donated their bodies to science, and then they practice on you and me, and that's just the luck of the draw, really. So there's the learning curve problem. It's a very difficult procedure, and it takes a lot of procedures to get good. Even then, when you're very good as a surgeon, it's very hard, right? So we're only talking of a few millimeters inside your knee, and these are metal instruments. And it does happen when they're fixing your knee. It's very easy to accidentally damage something else that was perfectly good before they got in there. And that's simply because it's very difficult. It's not because the surgeons are bad. It's because it's an extremely difficult procedure. So you're dealing with, very hard objects, the cameras and the instruments, and a very flexible leg that's kind of moving around. So the idea is to improve this situation by actually taking the tools and the camera away from the surgeon and having them. They're still there, and of course they'll still sort of control the robots, but the robots will hold the tools and the robots will hold the leg. So all the holding of everything is done by the robots in a very precise way, and the surgeons will then kind of direct what's going on, because it's the surgeons that have got the experience and the brain power to know what to do. The robots are simply precise. Then at the heart of this system, and this is what we're developing now, is the robot vision system that is figuring out what the camera is seeing, and it actually prevents the surgeon from accidentally hitting anything they shouldn't be hitting. So the cameras kind of work out the 3D structure, and this is all live inside the joint. and then the robot will only be able to move in the right location. And if the surgeon was to accidentally move in one way towards some perfectly good cartilage, the robot simply won't do it. So this is very much like autopilots in all the aircraft that we all fly in all the time. This is exactly how they work now. Airbus aircraft will not allow the pilots to do something bad. They just refuse. And the same can be done, and we can create robot assistance in surgery. So stay tuned, and you should see our experiments in the next few years. So that's where I'll end up. We can have questions in a second. I've brought 2 robots. They're on the back table, and after this talk, we can all have a go, and you can walk these robots around. We had one of our students program up a special behaviour in the robots, so I'll show you how to use it, and you can get some photos of yourself walking robots around and cuddling them if you want. Hopefully there's enough batteries and you don't wear them out. Okay, thank you very much.
Questions for Jonathan?
Jonathan, with the crown of thorns, do you teach? You said that you have the divers had a little camera on their thing.
Yeah.
With that, was there any learning involved where the camera was teaching the robot whether they got it wrong or right, or was it only just reinforcing that this is a crown of thorns each time?
It's reinforcing. It's known as reinforcement learning, actually. And we've kind of got the ground truth, because we know that where they finally sort of end up is a crown of thorns starfish. So they know that final point, it sort of, the system automatically gets an area from around that final point, and then it knows that this is the type of thing to see, and then it learns itself. And there's a whole range of these systems being developed at the moment that you can teach robots to recognise things. And they're known as sort of deep neural networks, and there are even systems that the engineers create the structure of the sort of the robot brain, but we then don't really understand how it does it. It's kind of a black box. So you create the structure, there's a whole lot of neurons in there, it's modelled on the brain. You then feed it a whole lot of information, say this is this is this, this is it, and it just gets better and better at doing it. And this has major ramifications actually for a whole lot of data analysis in the future.
So the process is just honing in and refining. It's not that it ever gets it wrong and says, no, that was a coral.
Yeah, correct, yeah. It's just a refinement process, yeah.
Thanks, Jonathan. Still on the crown of thorns, with the learning that the robot has, how do you factor in things like different light conditions and turbidity and things like that? So is it a longer learning curve for the robot?
Absolutely, yes. So with all these learning systems, you try and get the widest range of images that you can from different cameras and different conditions. And in fact, lighting conditions, that's the biggest challenge in robotic vision, is varying lighting conditions. And there are great examples so vision is being used a lot for these future driverless cars that we see in the press all the time. And why we're not going to see driverless cars regularly on our streets soon is because of this whole lighting conditions change thing. So you'll notice that you even probably find it hard to drive yourself in Brisbane when there is torrential rain and it's dark. It's very hard to see what's going on because the scene actually changes dramatically. It's a real, the road markings disappear because suddenly there's water and there's reflections, and that whole thing is very difficult. The good thing about the crown of thorns starfish is it is actually one of the easier cases. So it's in fairly shallow water, low turbidity, on the reef. So this is why we can tackle that now, because it's one of the easier things to do.
Thank you, Jonathan.
Thank you.
So that concludes the formal part of the program. We now have the opportunity for some robot walking and other things in the back of the room. So if you could please just join me in thanking our three speakers.
So everyone, it was just an opportunity to host you at QUT today to give you an insight into some of our amazing researchers. Hopefully it was interesting. Jonathan has kindly brought along 2 NAOs with him, but we also do have for you this afternoon a number of other things that we would really love you to interact with. We have a number of displays that has been part of the QUT Library Off the Grid program, so from QUT Library staff, including augmented reality, Raspberry Pis and a number of video creations. We've also got the State Library Edge with a couple of really interesting bugs. So we would really love it if you could have a drink, have something to eat, but also not only network amongst yourselves, but network with our technology as well. So hope you had a great day, and please enjoy the maker part of the afternoon. Thanks, Bob.